Hello, welcome to Intro to Cryptography. This is chapter 435. We will be using uh, what intro to cryptography. Okay, 435. We will be using Introduction to Modern Cryptography by Cards and Lindell as our book, right? The standard would be second edition, but you might be able to find some other online. We are going to be more or less using it as a guiding for guidance rather than a very precise thing that, oh, this is what we are going to do. I will oftentimes work with material that is not in the book or skip some of the material in the book in ways that I think would be suitable. This is a slash listed course between computer science and math and some other thing. I don't remember what it is. I think economics. But yeah, even if you're not very familiar with programming, that is fine. I'll be teaching this course slightly more from the emphasis of the math rather than the programming. However, I do expect you to be able to innovate, think of an algorithm for doing something. It doesn't have to be in a language, it doesn't have to be a pseudocode, but you should be familiar with some of the notation from computer science, for example, the big O notation and stuff. And otherwise, it should be a fairly easy course to understand, hopefully. Okay, so what is cryptography? Well, cryptography is the way to communicate secretly, right? Historically, it has been concerned with secret communications and how to send messages so that enemy does not understand what you're doing or someone else does not understand. You might just want to um, send it to a friend or whatever. The Oxford Dictionary defines it as Oxford defines cryptography crypt, cryptography graphy as the art of writing or solving codes, as the art of writing or solving codes or solving codes, right? And that is exactly what it historically was. A lot of times, you used cryptography to write messages and everything, and there was no scientific way of doing it. It was more or less an art. You had to be um, quite creative at it and have fun with it. Maybe there was no scientific way of saying, "Hey, this is how you should approach it always. This is how. This is what it means for a stricter code, what a harder code to crack, and all these things." Well, all of this changed in the late 20th century. Once you developed computers and modern computing, things suddenly became much more easier to break. Codes became much easier to break, and it became more and more important to be able to secure messages so that they can't be broken as easily. And that requires you to have some formal way of writing down what it means for a code to be strong or weak or anything. Okay, so what are going to be our course goals for this course? We want to understand what cryptography is and how to do it and how to use it properly. Okay, what goes on underneath your today's cryptography, how you should approach it. It's not going to be exactly cutting edge cryptography because this is a introduction to it, but something along the lines of how to understand cryptography and how to start doing it. Okay, and you should be able to create your own encryption systems uh, for smaller things. Not, I'm not going to say for banks or anything, but for smaller things that you will be able to use for your own real world uses. Okay, Now, modern cryptography compared to old cryptography is much bigger, right? In old days, you had classical cryptography was just sent for messages that you wanted to communicate to someone, maybe your partner, or maybe across war lines or whatever. Caesar used to, Julius Caesar famously used to use some sort of cryptography, coded messages with both his lovers as well as his military commanders, so that even if they're intercepted, no one would know what exactly is going on, right? But today we use it for many more things. You use cryptography even in your credit cards, for your banking, for emails, for everything, anything related to the internet. You're using cryptography, right? You want things to be secure, and so in modern cryptography, cryptography is basically design analysis and implementation of mathematical techniques of mathematical techniques for securing information, systems and distributed computations against adversarial attacks. So in this course, we'll not only be looking at how to make a system, but also how to attack a system, because the only way we know how to make something better is trying to see how we can break it. Okay. Well, historically, it has been an art, and historically, it has always been one-to-one. Okay. So in classical cryptography, all the things where, oh, I am going to send one message using some sort of an encryption to another person, and they are going to decode it with some key, right? And so person one, the classical cryptography has been what is called the private key cryptography. The private key cryptography. Okay. So what is the difference between private key cryptography and what is today called the public key cryptography? Okay, as opposed to public key cryptography. Okay, so what is a private key cryptography and what is public key cryptography? Well, let's start off with the classical setting and talk about private key cryptography first. So private key cryptography is you have a person one. They send a message to person two. Okay, and they encode it here. Encode with some key K, and this is decoded here. Decode with some key K. Okay, and now if there is an adversary listening from this point, right? Adversary, they're going to receive the encoded message, But without the key, they should not be able to figure out what we are talking about, right? They should not be able to figure out what the message is. So this is adversary. Adversary. Okay. So this process is called encryption. Encryption with a key K, with key K, and this is going to be decryption with key K, right? So you'll have some message M, which will be generally in plain text. Plain text message M, right? Which gets sent via, which gets encoded and is sent as a ciphertext C. So this is going to be my ciphertext C. Ciphertext C, and which person 2 gets, and they're going to decrypt by the their key, and I should have that M is equal to the decryption of my ciphertext. Sorry, of my ciphertext. Okay, so let me write what it means. So I'm going to say that C is equal to encryption, maybe capital, encryption of my message with the key K. Okay, and M should then be again the decryption of my message M with the key K. Okay, so if I'm sending a message, the encryption and decryption should be reverse process of each other, right? If I send a message, I encrypt it, I get some ciphertext, I decrypt the ciphertext, I should get my original message, right? This doesn't necessarily have to be from person 1 to person 2. You might just be storing some files on your computer that you later want to access on your own or something. You are saving some private data on your computer, in which case you are just encrypting onto a machine and via the message M. So this becomes C is equal to encryption by K of M. You're sending C. Well, the message received is again C, and now you use the key K on C, and you say, well, M is equal to decryption of K. So here, the most important thing is, in private key cryptography, is that the key has to be the hidden part, right? If the adversary knew the key, they would be able to reverse engineer what the message is, right? And that is a problem. I don't want my message to be leaking out, right? So the keys have to be hidden, but here's what private key encryption, and that is the important part of private key encryption. So private key encryption, CRYP encryption. Okay, private key encryption is going to be something where the key is hidden. A private key encryption scheme, a private key encryption scheme, scheme is defined by a message space M, defined by a message space M, and the algorithms and algorithms generator, encryption, and decryption. So far, I have in a way written down what encryption and decryption is. Let us talk more about all of them in general. What does the algorithm gen do? This is the key generating algorithm. Key generating algorithm. Okay, so you don't always want to use the same exact key. You might be wanting to use a key like if you're using the same key again and again, maybe it becomes likelier that the key gets broken. So you might have a lot of keys. You might have a page full of keys, and there is some algorithm you're going to use that you will say, oh, now I'm going to use this key this time, right? So generator is going to be some algorithm that outputs which key you're going to use. Outputs K, which is a key. Okay, so this is a key space that I'm going to have, and my key K is my key. My encryption ENC is my encryption algorithm. Encryption algorithm THM. And what does that do? Well, it takes the key K, takes key K and the message M and message M, which is in my message space, right? In my message space M as input, So it needs two inputs, and then it outputs the ciphertext C and outputs ciphertext C. Okay, so C is going to be my encryption. Okay, what's my message? What does decryption do? Well, decryption algorithm. Well, this takes the key, K, and the ciphertext C, and the ciphertext C, and as inputs, and it outputs the message M, and outputs M or error. Okay, if you feed it garbage, it should tell you, well, you are feeding me some garbage. Okay, so for AND, what is the major important thing? I can create set algorithms, great. And for all M and K, for all M in M and K output by generator, the most important thing that should happen is decryption of K of encryption of under K of message M should be back to message M, right? What is the entire point of encrypting a message and decrypting the message if the output is wrong? If I don't get back the same message. So this is the most important part. Okay, I want to encrypt my message, I want to decrypt the message, but I should be able to get it back. Okay, so now there are multiple ways of doing this, right? So the key is private, the key is known only to me and someone else. But now the problem is if the key does become known, if the message and the key does become known, I don't want my enemy to still be able to figure it out, because I have some encryption algorithm, I have some decryption algorithm. The adversary should not be able to figure out how to solve my code, right? And so, one of the first things about making encryption stronger than just like first way of saying, oh, this is a good encryption algorithm or a strong encryption, was given by Kirchhoff, and it is given by Kirchhoff's principle. Kirchhoff's principle. Okay. So, what does Kirchhoff's principle say? Well, first, the encryption scheme is not a secret. The encryption scheme is not a secret. Okay? So, the encryption scheme should be known to everyone. Anyone should be able to know that, hey, I am kind of using this encryption scheme to encode my algorithm. Okay, so the attacker knows the encryption scheme, knows the encryption scheme. Okay, the only secret is the key. The only secret is the key. Okay, and the key must be chosen at random and must be kept secret. Key must be chosen at random and kept secret. Okay, so as I was saying earlier, there are two ways of making sure a message is safe. One, even if someone knows the key, you should hide your encryption system. Or two, even if someone knows the encryption system, you should hide the key. So the Kirchhoff's principle says it is better to have the encryption system known and key kept a secret rather than key being known and encryption system kept a secret. Okay, and why? Why is this? Why is this the thing that we want? Okay, and here's the reason. Some arguments in favor of Kirchhoff's principles of this principle. Well, here's the thing. It is easier to change the key than it is to change the algorithm. Easier to change the key change key than change algorithm. Okay. If you want to change an entire algorithm, you have to think up of something completely new, how you want to encode in something, right? Compared to that, if you want to change the key, just take some other random key. Like if you're encoding by, let's say, if you're shifting everything by by 3 letters, shift everything by 5 letters. That's a new key. If you're completely changing the algorithm, it takes much more effort, right? So it's easier to do it. It is also easier to keep key secret than algorithm. Now, this statement requires some explanation. What does it mean by easier to keep my key secret than my algorithm? Well, you would say that, hey, it takes more effort to say out the entire algorithm than just say out the random key, right? But no. So historically, what is some way of how encryption was used? In wars and stuff, you'd be using the same encryption. You'd be using encryption to send messages throughout all your communication posts, right? You're sending one encryption to all the enemy units. All your uh, whatever message posts and everything. All of them would generally should be able to decrypt your message using the same algorithm. So everyone has the access to the same algorithm, right? However, if the message is coming from headquarters, it might be encrypted with one key. If it is coming from somewhere else, it might be encrypted with another key, right? Different outposts might have different keys of communication, so that even if uh, one key is broken, that does not mean all the communication is broken. That way, it is easier to keep one key secret, easier to keep a key secret than to keep algorithm secret, because if someone takes over, if someone defects from one station, they will be able to tell the entire algorithm, but they won't be able to tell the algorithm that some other station, they will be able to tell the entire algorithm and the keys they are using, but not the keys the other stations are using for their own communication, right? So that is what it means by it is easier to keep the key secret than the algorithm. And another thing is standardization. Standardization. Okay. What does that mean? Ease of deployment, and public validation. So I can give people the algorithm and be like, here's the algorithm we are going to use. Take this and go to your posts or wherever. And everyone has the same algorithm. Now you might give them like 700 keys and you tell them that, oh, we are going to use this key this time. And now you suddenly have a much stronger encryption system than trying to figure out, oh, I'm going to change my algorithm every single time. Okay? So that is why Kirchhoff's principles generally say, hey, it is okay if the attacker knows the encryption system. We shouldn't be super worried about the encryption system, the algorithm being secret, but we should be able to keep the key a secret. So even if they receive the ciphertext and the algorithm without the key, they should not be able to break it. Okay? The easiest example of a of encryption, easiest example of encryption is the shift cipher. The shift cipher. Okay, so this is the first example that we are going to look at, or maybe I shouldn't say easiest, first example. First example of encryption, this is the shift cipher. So how is the shift cipher created? Consider encrypting the English encrypting the English text. And what is going on? Encrypting the English text. Okay, and how do we do that? We associate A is equal to 0, B is equal to 1, C is equal to 2, dot, Z is equal to 25. Okay. Then my key k is going to be 1 of 0 to 25. Okay. And then I encrypt it to encrypt. Shift everything by k positions to encrypt using key k. Shift every letter by k positions of the plain text of the plain text message by k positions. For example, with wraparound. Okay. For example, suppose my message M was equal to hello. Okay. And the key I'm going to use is 2. So is C, which is equal to 2. Okay. So in that case, let me not call it C because I'm going to use C for the ciphertext. Is equal to 2. K is equal to 2. And then my ciphertext becomes, well, H is what? A, B, C, D, E, F, G, H. 8, right? 8 plus 2, 10. So that becomes Hij. E becomes Fg. J becomes Lmn. N, Q. Great. I have successfully got my message. Okay. And how do I decrypt it? So this is my encryption. Decryption is move shift every letter is shift every letter in reverse, every letter to the left by key positions. Right, so as long as you know the key, you can do this. And for this, we need a way of doing this properly. And so we need number theory. So formally, number theory. So what we are now going to define is going to be stronger and more useful than just for this cipher. And this is, number theory is the study of numbers. Like my research is in number theory, somewhere much more. And what I do is the closest actual application is modern day cryptography, right? Now, originally number theory was not introduced for cryptography. Cryptography slowly came from number theory because that is how a lot of things develop over ages, right? But here's what we are going to find. We will say let x is equal to y mod n if and only if n divides x minus y, right? i.e. x and y have same remainder when modulo n modulo n. Okay, so generally you would write x mod n is equal to the remainder of when x is divided by n. When x is divided by n. So x mod n is in the set 0 to n minus 1. Okay, this cannot be bigger than n minus 1. Okay, however, that does not mean that x and y can't be bigger than n generally. So for example, 25 is congruent to so the standard way of writing is actually congruent. I'm going to use that. Okay, 25 is congruent to, well, 35 modulo, let's say 10, right? However, 25 is not congruent to, well, not equal to, in this case, not equal to 35 mod 10, because this notation is equal to 5 mod 10, right? This is not equal, sorry, 5 mod 10. Okay, however, so this is just very basic notation of what happens. And what are basic properties? Well, if a is congruent to x mod n, b is congruent to y mod n, then a plus x is congruent to b plus y mod n. Okay, so let me say properties. Properties first. Second, if a is congruent to if a is congruent to x mod n, then m times a is congruent to m times x mod n. Okay, so multiplication is preserved, addition, subtraction is preserved, and in our case, for the shift cipher, the shift cipher formally, the shift cipher formally, it's going to look like this. First, if I go by how to write an encryption system, I need a message space. So my message space is going to be strings of lowercase English alphabet. Strings over lowercase English alphabet. Okay. Second, I need a generating algorithm. Choose uniform k in 0 to 25. Okay, so you want to choose a key uniformly from 0 to 25. Now, how do you encrypt a message? Encrypt a message m1, m2, ... mt. So suppose this is a T letter word or T letter message. how does it get encrypted? Well, output C1 C2 dot 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 CT, where CI is equal to, I'm putting the square bracket notation, MI plus K mod 26, right? Why mod 26? Because we have 26 letters. It will wrap around after 26. And for decryption, using K of C1 C2 dot 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 CT, output M1 dot dot dot, no comma, M1 M2 dot 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 MT, where MI is equal to CI minus K mod 26, right? So for example, if my key was 5, K was 5, and CI was, let's say, D, then value of D is going to be 3. D minus 5 is going to be 3 minus 5, which is negative 2, which by modulo things is 24, right? And that would be 25 is Z, so 24 would be Y. Okay, so easy to verify, easy to verify that decryption K of encryption K of M is equal to M. Okay, so it is correct. Great. So now, while we haven't yet actually defined what it means by code to be secure or not, we want to know, hey, is this really secure? Okay, and question. Oops. Question, is this secure? Well, answer, I haven't actually defined to you what secure means, but you can see that this is really not secure. No. Right? Sure, a normal person instantly would not be able to recognize this as a coded message, and they might think, oh, I have found some gibberish. But if you know that you're looking for a message, there are only 26 possible keys. Only 26 possible keys. Right? So given how would you decrypt a message? Well, given a ciphertext, you can just try decrypting with every possible key. Try decrypting with every possible key, and at least one of them should make sense. One possibility should make sense, right? So even if my key is not known initially, well, even if this attacker right here in my image, where is it? So far up. Even if this attacker right here, adversary, Mr. or Mrs. M or whoever, this person, even if they don't know my key, they can just brute force down my code to till they find some meaningful answer, right? And that means this is not really suitable, right? So this is an example of a brute force or exhaustive search attack. Example of a brute force or exhaustive search search attack, right? And so let me give you some exercise. I'm going to give you a ciphertext. Ciphertexts. TQXXA IA DXP. Try to decrypt this ciphertext and tell me how long it takes you. Okay, so I'll stop this first lecture here. So this is just an introduction to things. So this is our first example of how to encrypt a message, how to decrypt a message. Tomorrow we will see how to make what are some stronger algorithms, how you define an algorithm to be strong, what are you looking for in cryptography. You can't really say an algorithm is strong without having some idea of what strong means, right? So all of these things we will start defining tomorrow. Okay.